All right, everybody, let's review some energy stuff. And then we're gonna switch gears a little bit and talk about more about reactions and classifying reactions. I'm doing this, covering the material in sort of like two tracks at the same time, but here we're talking about energy and phase change and almost like individual molecules and how they interact. And then our lecture today, our new material is about classifying reaction. Then we'll be able to fuse the two together and use them to explain a lot of these concepts together to explain a lot of things. But it might feel a little bit disjointed, like we're jumping all over the place for now. Trust me, it does all come back together at some point. So let's start with talking about phase change and energy. So if we start, what are the two axes, I guess, for a heating curve? It says draw a heating curve. And heating curve, remember, is not actually curved. It's really a series of straight lines. But basically, it's plotting two variables against each other. What are those two variables? Not time. Don't mix up your capital T and your lowercase t, right? Temperature. And so temperature is what's going to be here. What are we changing down here that's changing the temperature? What are we doing to change the temperature? We are kind of giving it time, but more specifically, if we think about like taking a piece of ice and putting it on a hot plate, it's not just the time that's causing the ice to melt, it's the heat, energy in. So Q in. Right, so when we dump energy into the system, first off, where are we starting? Yeah, at time equals 0, then Q is 0, right? So we're starting right here, and we're starting at minus 23 Celsius. And when we dump energy in, what's going to happen initially?
Right, like consistently.
Yeah, and you might notice too that I have a different specific heat for ice. Turns out even though ice is still water, it has a different specific heat. It actually takes half the energy to warm up ice as it does to warm up liquid water. Liquid water just has more attractive forces in between the molecules. The point that speeding them up to increasing the energy of those molecules is actually harder when it's liquid. Yeah.
Would you have to use two equations then?
That would make sense, right? Because we're gonna have the ice changing temperature at one point, and then after that, we're gonna have water, liquid water changing temperature. And since they both have two different specific heats, we're gonna have two different Q equations there. And related to that, what can we say about the slope of this heating curve for when it's ice versus when, I guess first, where is the temperature rising going to stop?
It's
0 C, because what happens? It starts melting. And once it's done melting, so that's going to take some amount of Q. This is supposed to be all horizontal. Imagine that this is perfectly horizontal. When it gets to the point where all of the ice is melted, temperatures can start rising again, right? Is that slope going to be steeper or shallower? Yeah, because for the same amount of energy, the temperature is not increasing as much, right? So if I was asking this question on a test, I wouldn't expect you to draw it to scale or get the slopes right. I'm mainly interested in, is the temperature changing or is it at a plateau for a phase change? But you can actually plot this all really pretty well. And in fact, you can make a graph like this in Excel and get it all perfectly to scale if you wanted. Put in your mass, put in your specific heat, and then just make a column of Q in where you go 1, 2, 3 for in units of kilojoules. Yeah.
Still do that for you.
You just have to type it in. So if we set up a column of Q in and we just filled in 1, 2, 3, 4 down however far we wanted, then we could have temperature and we could say, okay, well, temperature is, or we could say delta T would be the easiest way to do it. Right? Because if we start with Q is in this column, right? Delta T is just Q over mass times specific heat. So we could write the equation, say, equals, I don't know, whatever this column is, call this A1. A1 over our mass, which is 35 grams, times 2.11. And we can just copy and paste that formula into this entire column. Where Excel gets tricky is Excel won't intuitively know, it's not built to understand that when you get to 0, there's going to be a phase change. So this discontinuity part, you would either have to program that in separately, do it by hand. But yeah, you can plot this line and then you can basically take this equation and say, and write another formula. Because basically what you're doing with Excel is really basic programming. So you can actually have next column be temperature and write an if statement. Say if temperature is less than 0, then then your delta T is equal to this.
Oh, and then you can like tell it to plateau.
And then you can tell it to plateau by using if statements, because Excel has if statements built in. Yeah, Gloria. Just the character. You can copy and paste the character from, if you just Google delta character. The old school way of doing it is, Windows actually has what's called a character map built into it. Before we had the internet for finding all these things, you actually had to go to the character map, which is basically just a list of all the different icons or all the different things that a font had stored. And you would go and you would find the Greek letters section, and then you would copy the delta and copy and paste it into your thing. I bet they still have a character map that's kind of out of date. It's in the interest of history. Yeah, there's a character map. So before you could just Google things, you would go in here and say, look, this one looks a little different than the one that I'm used to these days, but there's going to be a section that's the Greek letters. There it is. So we find delta in the Greek letters section. Right there. You copy, then it's on your clipboard, and then you can copy and paste it into something else. This is before, and now even Word has insert character built into it, so you don't actually have to do it longhand anymore. But I don't think insert character works in Excel. If you're in Sheets or if you're in a Word document, then you can do it like that. But anyway, things that you don't need to worry about learning because they're somewhat obsolete. So where were we going with this? And frankly, if I was doing this, if I was just writing this formula for myself and I was just labeling the columns myself, I would actually I'd write it just like that, because then that works just as well. If I'm not submitting this for publication or something like that, then I don't really care. I know what I mean. As long as I'm not going to show it to anybody else, that's perfectly fine. And maybe it's just because I'm kind of a big nerd, but it is kind of a flex in adult world to be able to send somebody a spreadsheet that has everything perfectly formatted with really elegant formulas written into it. I like to remind people how smart I am by sending them really intricate spreadsheets that are way more work than I need it to be, but it reminds everybody why I'm good at what I do. That's mostly just my insecurities though. Anyway, stuff that's relevant to you. if we want to know the final. Are we done with this heating curve for part one anyway? Yeah, final temperature, but yeah, pretty much. Our final temperature is 22 Celsius. We're good. The heating curve isn't all that useful on its own. It's useful for understanding the basic ideas of what's happening and in what order. And where it's really valuable is for part two. If we want to know what the total amount of energy is when we get to this point, we're basically saying we want to know what this X value is once we get to 22. If we want to know what that is, again, if we're trying to do it in Excel, we'd have to do it piecemeal and it'd be kind of messy because we'd have to do 3 different functions and if statements and stuff like that. It's actually one of these things where it's actually easier to do it by hand. And I don't say that about spreadsheets very much. But in this case, if we want to know what our final Q is, our total Q, it's really the sum of 3 different functions, right? Was it DM that asked about if we have to do Q twice now? Do we have to do Q twice? Yeah, we have 2 different segments that are changing temperature, right? We have 2 different segments that are changing temperature. You know, Q1 and call it Q1 and Q3. For Q1 and Q3, we're gonna get 2 different heat values, right? Because we have a different delta T. We have the same 35 grams of water, but we're gonna have a different delta T and a different specific heat for Q1 and Q3. So we want to know the total amount of energy that we're dumping into this system. We're gonna have to add all of these pieces together. And then we've got Q2 as well. And Q2 is a little bit, it's actually simpler, but it's different. So we have to remember what's happening with Q2.
It's just
It's just
going
plateauing.
straight.
It's plateauing, so how are we getting a number for Q2?
down.
You don't just keep it what the last one ended.
There, for the temperature there isn't, but what about if we want this energy? It's melting, right? So when it's melting, that's what this was, remember?
Yeah.
Delta H of fusion was the energy that it takes to melt 1 gram. Again, sometimes you'll see it written in joules per mole. In this case, it's in joules per gram, which makes our life really easy.
Yeah.
So for Q2, we're just gonna say, okay, well, we've got 35 grams of ice. And every 1 gram is 334 joules to melt it. If our enthalpy of fusion was given in moles, then we would just have to take the grams and convert it to moles first, but we know how to do that. That's not tricky, right? It's just 1 extra step. So getting a number for Q2 is pretty straightforward. Getting a number for Q1 and Q3 are each pretty straightforward as well. The trick for this problem is just one, knowing that it's going to be 3 different steps, and then knowing to get your final total heat means adding all of them together. Our total X value is the sum of all of our X values added up, right? So Q1 is when it's still ice. It's 35 grams. Use the specific heat of the ice, 2.11 joules per gram degree Celsius. And delta T, final minus initial. So the ice stops changing temperature once we get to 0 Celsius, right? So we're going from -23 to 0. That looks really familiar, right? We've done a bunch of these Q problems now. Q3, it's going to be the same 35 grams. different specific heat, because now it's water. And different delta T, because we're not heating it up to 23 Celsius, we're only going to 22 Celsius. So we can get numbers for all these. We all are working at getting better at plugging things into our calculators without making typos, right? No, kind of. 334 is about a third of a kilojoule, right? So a third of a kilojoule times 30 is going to give us about 10 kilojoules plus another, so it's what, 12 kilojoules ish, right around 12,000. Who's got a calculator out?
11,690. Joule.
I'm gonna just put it in kilojoules, so it should, so that I can avoid putting it in scientific notation. But if you're writing in scientific notation, 1.17 times 10 to the 4 joules. Here we're gonna get a lot smaller number, right? 35 times 2 is 70 times another 20 is gonna be like 1,400.
Wait,
35 times 2.11 times 23.
1,698.
198.
198.
So 670. Typically, this is why we see things reported in kilojoules all the time. It turns out a joule is just a really small amount of energy. Kilojoules usually makes more sense. And this, because our specific heat is just about double. Our answer here is going to be just about double, something like 3 kilojoules. Times 22.
Yeah, 3,221.62. 3.2.
Give me one more sig fig.
It's 35.0, so 3.2. Right?
3.22.
3.2. Gotcha. Thank you. Turns out that the hardest part of standing up here is not the mental arithmetic, it's actually trying to round sig figs in your head. All right, it's going to be 10 to the third joules, so 3.22 kilojoules. Final step is just adding them together. We calculated all the steps individually, so the total energy is just the sum. $11.7 get 13.4 plus another 3.22. Unless the question asks, they're both valid answers. So whatever is easier. If it's easier for you to do everything in scientific notation and not have to convert to kilojoules, that's fine. If it's easier to put it in kilojoules, do that. It would only be 3 sig figs. Good catch. Because this number was plus or minus a tenth of a kilojoule.
Isn't it just like one?
So it's, yeah, it's really to keep the same decimal places. This one goes to the 10th place. So even though both of these go to the 100th place, we're going to round to the 10th place because we switched to adding. the size of these numbers surprising? Like relative to each other? This one's almost 10 times greater. It takes almost 10 times more energy to melt the ice as it does to warm the ice up to freezing. I always found that surprising to me. It seems like, yeah, it seems like it would take more time and energy to get it up to temperature than it would to actually do the melting. But it turns out there's a lot of energy in phase change. This is why it's so effective to just put a bunch of ice in your drink to keep it cold. Because when you do that, you make that whole system is going to try and stay at 0 Celsius until all of the ice is melted. It turns out that actually takes a lot of energy.
Is that because water is higher than ice does?
It's so if you took the same amount of water and ice and they were in a similar situation where we, our room temperature water was 23 Celsius and our ice was at minus 23 Celsius, the ice would warm up to 0 faster than the water would cool down. But because then there's that next step of phase change, the phase change is what's going to keep everything at 0. It's going to keep cooling down that warm water until the warm water also gets to 0 Celsius. And then everything will stay at 0 Celsius until all the ice is gone. Assuming perfect mixing. It is true. The problem with that is that warmer water doesn't taste as good as cold water. Because if you actually use hot water and you fill an ice cube tray with it, it tastes like the inside of your water heater, which is less than ideal. So same for boiling water. Even though it would be faster to boil a pot of water starting from hot water out of the tap, that's not the way chefs do it because you don't want your pasta to taste like the inside of your water heater. But yeah, hot water, and they're not entirely sure why that is, but hot water actually does freeze faster than cold water. And likely, I'm speculating here, but it's likely because when it's hot, you get more evaporation happening off the top of the water faster. And evaporation's a phase change, right? And if some of the water is evaporating off the top, that's cooling down the rest of the water that's sitting there faster. So you actually wind up cooling down the surface faster by starting with it being warm. Yeah, they've measured that. And you can, it likely also has to do with the convection, the currents that are inside the ice cube as it's forming. When you still have the liquid center of the ice cube, you have a temperature gradient between the outside to the inside. It's coldest at the outside and it gets warmest in the middle. If it starts warm and you create a larger temperature gradient, you actually cause more mixing because the water will naturally mix better if you have a bigger jump between cold water and hot water. That instinctively causes not instinctively, but that automatically causes mixing due to the difference in densities. So it's probably a combination of those two things, but it's really counterintuitive. And that's one more reason why we're not going to get much into rates in this class, because it turns out as soon as you start involving time, that actually is a whole different ballgame. We're just talking about time was nowhere in here, right? We just looked at actual total amount of energy and temperature. When you involve time, that's now are involving calculus. Because the rate of heat change depends on the difference in temperature between the inside to the outside and how fast it can transfer. And that's a whole field of study in grad school if you go to grad school for chemical engineering. I took a whole year of classes in grad school just on rate of heat transfer between objects. Because it turns out that's kind of important when you're designing oil refineries, for instance. Yeah. Yes. Well, partly because of who I hang out with, but my good friend at the college is he was an oceanography grad student and then left to become a pure math grad student. And he likes to say, when he wants to say someone is 100% wrong, he'd say that they're off by pi radians. But that's just him. He's weird like that. He just refuses to use degrees in any circumstance. And so instead of saying 180 degrees off, he'll say pi radians off. But no, we do, and because it turns out that trigonometry and breaking down triangles is a really, really big part of physics. If I push something at a diagonal, if we define the top of this desk as our XY plane, if I push something at a diagonal, if I want to know the total amount of force I applied, then I have to use Pythagorean theorem and figure out how far I moved this and at what angles. And if I want to know how much of my force was in the X direction versus the Y direction, you actually have to use trig and the unit circle, well, sine and cosine anyway, to actually calculate that. So if you're going to do anything related to physics, 100%, you have to be able to do what's called vector analysis, which is basically taking a force in 2 dimensions and breaking it down into, here's my X component, here's my Y component. So it does show up. You don't need to have it memorized necessarily. It's still helpful. What did I do I used something the other day where I was looking at using special right triangles. Oh, we were calculating the distance between third base and first base for my son. He likes being third baseman, so we need to pace off what the distance was from third base to first base in our backyard. And so we had to look at the difference between first base and home plate, figure out that distance, and then use Pythagorean theorem and special right triangles to figure out what the hypotenuse was between first base and third base. Do you have to do that? No, but it's nice to be able to get it right. You can go to a field and measure it. That's probably more work though than just sitting down with a piece of scratch paper for 5 minutes. Plus, then I get to teach him about the Pythagorean theorem. That lucky kid. All right. So key takeaways from this practice problem. 1, if you have a temperature change, you're using our Q equation. Q equals mass times Cp times delta T. If there's no temperature change, but you still have energy change happening, or if you have a chemical reaction, the most basic of which is a phase change. Phase change gets described as being a physical change a lot of time, but we can still write it as a chemical reaction. And it turns out all chemical reactions have a difference in energy between where you start and where you end. All right, where you start and where you end for a phase change might look like H2O solid turns into H2O liquid. Easy enough to write it that way, right? And then we can say delta H for that reaction is 334 joules per gram. But that means that we actually can write any chemical reaction. It's going to have an associated energy change with it. Almost no chemical reactions are actually net zero in terms of energy, which means we can actually figure out how much energy a reaction gives off based on stoichiometry. So we're going to basically tie reactions back to stoichiometry, or sorry, take energy and tie it back to stoichiometry. Because if you want to know how much energy it's going to cook a tri-tip, and all you have is your enthalpy of combustion of propane, you can work backwards to say, okay, my tri-tip is this size and it takes this much energy to cook a pound of tri-tip. I need to put this much kilojoules of energy into the tri-tip for it to be cooked, which means I need to burn this many moles of propane, which means this many pounds of propane. So you can actually predict before you turn on the barbecue whether or not you need to go refill your propane tank. Now, that's a lot even for me. I don't actually do that. I just turn on my barbecue, and if I run out of heat and halfway, I just finish it on the stove. But you could, and some people do. And actually, if you're doing this like if you've all heard of the fire festival, right?
Yeah.
It's a really, really dramatic example of how really bad planning can ruin a whole bunch of people's month. It was a music festival that was supposed to take place on a private island in the Caribbean. They collected all this money for the tickets, and then it turns out that the organizer was either, stealing the money or just didn't plan ahead well enough because they ran out of like everything. They had, 10,000 people and, 20 porta potties, for instance. Obviously, that's not chemistry per se, but if you could think out, okay, one porta potty can serve 20 people. That's enough right there to be able to say, well, obviously, if I have 10,000 people, I need 500 porta potties, right? That type of logic is really what we're practicing here. We're just doing it with chemicals and energy. It's the same type of logic, right? And if you are going to do something like cater an event, then knowing how much propane you need to buy before you get to the event might be kind of important. All right, so speaking of reactions, let's talk about some different types of reactions. I guess I'll open it up. Any other questions about energy, random or otherwise? Okay. Don't worry, we'll come back to energy. So you'll have another chance to ask them if it occurs to you later. So if you look at this level of chemistry is frequently called general organic and biological chemistry, GOB chemistry. It's sort of the intro level chemistry. If you just need like a really broad idea of how chemistry applies, if you're, say, a nursing student or something like that, you take this level of chemistry called GOB chemistry. This is the first part of that. This is intro to Gen Chem. If you look at a GOB chemistry textbook, you see a classification of reactions. It might look something like this. Where it has terms like synthesis reactions, just means that you start with two things that are small and you make something big. Decomposition means you start with something big and you make it small. Or you have single replacement, where you start with two molecules and you end with two molecules, but one of your atoms switched hands. Or you can have that happen twice. I don't really like these type of descriptions though, because one, all the different GOB textbooks I've looked at, they all have their own version of this. There's no like cohesive, authoritative viewpoint of this is how we're going to define reaction. Don't bother taking a picture of this, Asen. I appreciate that, trying to save yourself some time, but my next step is going to be, well, because there's no comprehensive agreement about what this classification should be, there's also classifications like this, where you've got precipitation reactions, acid-base reactions, gas evolution reactions, just means that it bubbles. Oxidation reactions means that something's rusting. Combustion reaction means something's burning. This is also another really common way to look at it. But then if you switch what textbook you're looking at, there's even simpler versions. Addition, decomposition, or neutralization. None of these really mean, they're all using real chemistry words, and they're using them correctly, but they're not, like, there's so many different ways of looking at chemical reactions. For instance, if you were a organic chemist, you would look at something like this, where you have substitution, addition, and elimination, and you have electrophilic, nucleophilic, and radical-based mechanisms.
Yeah, so like in Chem 1 today, we did sodium bicarbonate and acetic acid.
Right.
What is that?
So that's, you could classify that as neutralization. You could classify it as an acid-base reaction. It is both of those. It's also a gas evolution reaction. This is kind of my point though, right? There's so many different ways to look at even something as basic as vinegar and baking soda. Right? And basically the more zoomed in you get, the more different ways you need of classifying it. I heard somebody laugh at the idea of radical reactions. Turns out radicals are a real chemistry term. A radical just means an unpaired electron. So if you've heard of free radicals, they were big in the news a while ago, not really in the news so much as like in health trends. eliminating free radicals from your diet, or don't heat up your leftovers in that type of Tupperware because it generates free radicals. Those are a real thing. And they're radical. They're radical in the sense that they're exceptionally reactive and unstable, not radical in the sense that they're enacting social change. So, but like when you take my OChem class, you're gonna start, like, we have hit every single one of these types of reactions in my OChem series from this point of view. We also talk about the other types because we lay the foundation for them. But since this is the very basic starting point of chemistry when it comes to college chemistry. Oh, there's one more in here. This is a far from complete view of looking at the way that different enzymes catalyze reactions in biochemistry. So to a biochemist, this matters more than any of this stuff. And to an organic chemist, they don't care about this at all because biochemistry is not real chemistry to them. I'm putting words in their mouths, but it's messy. Biochemistry is messy, so it's more like stamp collecting than it is actually understanding what's going on. We're going to start at the very basic sense. When we're classifying reactions for this class, there's two main types of reactions. Everything else comes from those. When you have a chemical reaction, either electrons transfer between different nuclei or they don't. That's an easy way to classify things. If the charge on atoms changes, it's what we call a redox reaction. All right, anybody who's had a chemistry class before know what redox stands for? It's not an acronym, but it is an abbreviation. Redoxidation. Yeah, it's oxidation and reduction. Yeah. Sometimes you just got to throw it out there and you wind up getting right. Oxidation reduction reaction. For whatever reason, we say oxidation reduction, but when we abbreviate it, we switch the order. Don't ask me why. That's just a weird idiosyncrasy of chemists. If they don't, then a strong argument could be made for saying that if electrons don't transfer between atoms, it's not really a chemical reaction. If electrons don't transfer between nuclei, if it's not a redox reaction, it's really just rearranging all the pieces you already have. You're not really changing where the electrons go. So there's not one cohesive definition for reactions that are not redox reactions. You could just say not redox, probably makes the most sense. I tried to come up with a good way of defining it. I found a couple textbooks that call them complexation. Yeah.
How would if you're given a reaction that ends up with the same amount of electrons on each side for each individual atom, how do you know if those atoms for the electrons to switch places?
That's exactly what we're going to go into next. So sometimes it's really obvious. Sometimes if you have something like sodium metal and we'll just use aluminum ion. If we have these two things reacting together, sodium is way better at giving away its electrons than aluminum is. They're both more stable as a charge, but sodium is way less stable when it's neutral compared to aluminum. The ionization energy for sodium is much lower. So what happens when you put these together is you make sodium ions and aluminum. So this type of reaction is really easy to see. The electrons are changing hands, right? You've got sodium with no charge here and then sodium with a charge. It must have lost an electron. You got aluminum with a charge here and it's neutral over here. It must have gained some electrons. Is this reaction balanced the way it's written? The atoms are, but what's wrong with it, DM? Yeah, even though we had the same number of atoms before, now the charges are balanced too. And if we really have a balanced reaction, the charges have to be balanced too. Otherwise, we have a mismatch in the number of electrons. We lost electrons somewhere. We try not to do that. It's always going to look balanced if we've done it right. Right, so this is a really obvious example of a redox reaction. Happens really quickly. In fact, it happens explosively. If you mix sodium metal with aluminum ions, this reaction happens so quickly it'll probably catch fire. Sodium as a solid, as a metal, is really unstable. Like if you just drop it in water, it emits hydrogen gas and puts off enough heat that the hydrogen gas catches on fire and sometimes explodes.
We should do that.
Do we do that one? Do we have solid sodium here, Kyle?
And potassium.
And oh, we have some potassium.
We do.
Yeah.
Get rid of it.
We'll do it up here. I will do it. Actually in the fume hood, or maybe I'll bring the blast shield from. We have a blast shield at the college specifically for demonstrations like this, so everybody can see it. Potassium. Remember back to your periodic trends. I know it's been a while. Where do you have really low ionization energies? On the left and in the bottom, right? So sodium is so reactive that when you drop it in water, it catches fire. Potassium is so reactive when you drop it in water, it doesn't even stop to catch fire. It basically just pops like a firework. Which if you think back to the flame test, potassium also is that kind of pale pink color. So you actually get like a pink firework, which is really fun to watch. And then it disappears. It doesn't really disappear though, because it winds up just dissolved in the water. But so redox reactions happen really quickly. Sometimes they're really obvious when it comes to recognize them. Anytime you can look at ions and you can tell the ions change charge in the course of the reaction, that's a pretty good chance that's a redox reaction. There are situations where it doesn't appear to change charge. For example, a subset of redox reactions are combustion reactions. You take methane and you let it react with oxygen, you get CO2 in water. That doesn't look like anything changed charge because everything's neutral before and after, right? So to explain whether this is a redox reaction or not, we're going to use what's called oxidation states, which I think you'd heard about briefly last week at some point. So oxidation state is basically treating everything like it's an ionic bond. We know that this is actually a covalent compound, right? Where the electrons are being shared because it's made up of two nonmetals, right? And nonmetals all want to gain electrons. But basically what we do to assign oxidation states is we essentially just say, okay, well, this carbon is more electronegative than the hydrogen because it's closer to fluorine on the periodic table. If it's more electronegative, it gets first dibs at the electrons. And you basically just say, okay, well, how many electrons does carbon want to gain to have a full valence? 4. So if the carbon had first dibs on the electrons, we just say, let's treat it like it's a -4 in this case, which would make the hydrogens what? Positive. They have to add up to 0 now, right? Each of the hydrogens is going to be +1, and there's 4 of them. What's the oxidation state of the oxygen going to be here? It wants to be -2. Why do you say 0, DM?
0.
Because oxygens are they're both equally strong, right? You're right. I'm just looking for the logic behind it. if it's O2, if they're both equally strong and their charges have to add up to 0, what do their charges have to be? They've got to be 0. Right? You can't have one of your oxygens with a +1 and one of your oxygens with a -1. So, and the other way we describe is anything in its elemental state has an oxidation state of 0. Sorry, I didn't mean to embarrass you. I want to know your thinking. And because I was told so is a perfectly reasonable explanation for right now. What about on this side? What happened to the carbon? Carbon's not with hydrogen anymore, right? It's with the oxygen. And which of those is more electronegative? Oxygen's more electronegative now. So the oxygen wants to gain its electrons. Each oxygen needs to gain 2. Like we just talked about, right? So if there's 2 oxygens and they're both -2, what does carbon have to be? +4. So if your carbon went from -4 to +4, the charge changed. It lost electrons to do that. So the definition of something losing electrons, we call that process oxidation. So oxidation means oxidation is loss of electrons. It is a clever-ish acronym that helps us remember this. Oil, and if oxidation is loss, reduction is gain. So oil rig is one way to remember this. The other way you can remember it is a little bit more fun. Is Leo the lion says Gur. Leo, losing electrons is oxidation. Gaining electrons is reduction. So what's been oxidized and what's been reduced in this reaction now? The methane is being oxidized, most specifically, the carbon in the methane is being oxidized. Because what's our oxidation state of our hydrogens in the water? So there's 2 of them and they're each +1. Because your oxygen is -2. It's more electronegative. Electronegative gets first dibs. So your hydrogens went from being +1 to being also +1. So your hydrogens didn't change oxidation state. They were neither oxidized nor reduced. Your carbon went from -4 to +4, so it was oxidized. Your oxygen went from 0 to -2. So your oxygen was reduced. So before we started explaining this process, we started with the question was, how do you know if it's a redox reaction or not? If your oxidation states change, it's a redox reaction. So there's some types of redox reactions that are really fast to recognize. And then there's some that always look the same. Once we've done the work of showing that this combustion reaction is redox, we can just say, oh, it's a combustion reaction, therefore it's also redox. Right, so this is going to be your foolproof way of determining, is it redox or is it not? Right, I know I wrote the word complexation up on there on the board, and it's in the slides too. But I'm actually totally okay just calling the complexation reactions not redox reactions. That would make sense too. what I was trying to come up with, why I like the term complexation is because it's just another way of arranging things, but nothing's changing identity. If you started with aluminum 3 ions and it goes through a complexation reaction, you still have aluminum 3 ions. So rearrangement would be another good way to say it, or just straight up not redox reactions. Right, and so the four most common at this level terms that you see is for redox reactions, you have metal redox reactions. That's where if you're starting or ending with a metal, then it's usually really straightforward to see. And then if it's a combustion reaction, that's really easy to see. This is not an exhaustive list, though. There are redox reactions that are neither of these as well, though. In fact, I know some of you have taken AP Bio, right? What's an example of a redox reaction that happens in a cell? Give you a hint. You can just give me the general gist of it, but most metabolism reactions, like photosynthesis. Photosynthesis works. Cellular respiration is a collection of reactions. They're not all redox reactions. But if you look at your at the Krebs cycle, the citric acid cycle, any of the steps that made NADH or FADH2 or used FADH2 or used NADH are going to be redox reactions. The entirety of the electron transport chain pretty much is redox reactions. But they're not really metal redox necessarily, and they're not combustion reactions. They can get summed up as combustion reactions, but they are, a lot of them wind up being transferase reactions or oxidoreductase reactions. They actually have their own specific term. A lactate dehydrogenase or alcohol dehydrogenase is going to catalyze a redox reaction, but it's not one of these other classes right here. Right, and so from that point of view, from the biochem point of view, I give biologists and biochemists a hard time, but from a biochem point of view, all of the rest of those cycles and processes are just to set up the redox reactions. All of the isomerases and all of the rearranging that has to happen is just getting it set up so that it can get to the next redox reaction and make more NADH. It doesn't go away just because you're done with the test, does it? In the other class even. All right. In terms of these non-redox reactions, rearrangement reactions, the two types that we're going to talk about most are going to be precipitation reactions, just because they're really common in everyday life. And also they're pretty easy to recognize once you know what you're looking for. So they're sort of a staple of this level of chemistry. One of the first reactions that you learn how to classify your precipitation reactions. And then acid-base reactions, partly because biochem depends a lot on having the right pH and having the right acid-base reaction happen at the right time. Winds up being really important. All right, so here's our general categories here. For these complexation reactions, if it's an acid-base reaction, these can be a little bit tricky because they look on the face, they kind of seem like they might be redox reactions at first. There's several different definitions of an acid, but the most basic one, no pun intended, is transferring a single H+ atom. If you move a hydrogen ion from one molecule to another, it's an acid-base reaction. Because but that doesn't qualify as being a redox reaction though, because how many electrons does a hydrogen ion have? 0. Hydrogen, when it's neutral, has one electron, right? If it's got a positive charge, it's just a nucleus with no electrons. So it's not a redox reaction, even though it means the charge on your overall molecules might change. So for instance, if we put nitric acid with sodium hydroxide, we get water. And sodium nitrate. And if we break down what's actually happening here, when we put an acid in water, if we put a strong acid in water, what we actually get is hydronium floating around plus the nitrate. And if we put sodium hydroxide in water, we don't actually have sodium hydroxide floating around. We get the two separate ions floating around. We get sodium ions floating around and hydroxide floating around.
Naturally tend to go into sodium hydroxide.
Yeah, so when you put ionic compounds in water, why the reason that they actually dissolve is actually because they're being split up and held apart by all the different water molecules. Basically, your sodium ions are going to get surrounded by all the negative charge, all of the extra electron density from the oxygens, which will make more sense next week when we talk about polarity. But basically, all the water molecules get in the way and they surround these ions. So you otherwise, if you had a solid ionic compound, it just wouldn't dissolve in water. And some of them do that. Some of them are so strongly attached together. If you try to dissolve, say, mercury sulfide in water, it's just a rock. It just sits there. Nothing changes. But if some compounds, when you put them in water, they dissolve and they turn into these separate ions. And if you do that, if we put these two things together, the hydronium and the hydroxide kind of wind up sticking together a little bit. Basically, the hydronium is not super stable on its own because it's got a positive charge on an oxygen. The oxygen's sharing electrons more than it wants to. And a hydroxide over here, the oxygen has a negative charge. If you put hydronium and hydroxide together, you get two H2O molecules. The hydronium gives the hydroxide an H+. And that makes everything more stable because now we have two water molecules and now the charge on everything is 0. Everything's more stable. But even though the charges changed, no electrons changed hands. If we look at the oxidation states here, the oxygen is -2 over here. And it's still -2. The oxygen's a -2 over here. And it's still -2. So because no electrons changed hands, even though the charges changed, the charge of the entire molecule changed, all we did was we moved an H+ from a hydronium to a hydroxide. So it's an acid-base reaction, but it's not a redox reaction. That other example we were talking about earlier, vinegar and baking soda. Who knows the formula for the acid in vinegar? What is it? Or the name of it? Yeah, acetic acid. So, which means acetate, which is, who remembers your polyatomic ions? C2H3O2 with a -1 charge. And if we make an acid out of that, we get acetic acid. If we put that with baking soda, what's baking soda? Sodium bicarbonate or sodium hydrogen carbonate. If you let those react, the acid gives an H plus to the hydrogen carbonate and makes carbonic acid. And then now you have an acetate and you still have a sodium around. So you make sodium acetate at the same time. So all that happened is we moved an H plus from the acetic acid to the hydrogen carbonate. Now, what actually happens in real life when you mix baking soda and vinegar? Bubbles up, it fizzles. It's not very fun reaction, but it's better than nothing, I guess. And that turns out that's actually because the carbonic acid, when you have too much carbonic acid dissolved into water, it naturally splits up into CO2 and water. Because if you look at all of the atoms here, that's one water molecule plus a CO2 molecule. If you add up, you get H2CO3. So our carbonic acid is really just CO2 with the water stuck to it.
How does that turn into acid?
Keep going.
If you had like the water that's stuck to
So if we, yeah. So basic carbonic acid's Lewis dot structure looks like this, which means it can actually lose one of these H pluses pretty easily. And then you get hydrogen carbonate, where everything's neutral except for this oxygen. And if you take another hydrogen away, you get just regular carbonate that's got an overall -2. Right, and this is actually the reverse of this, is what happens when you carbonate water. You carbonate water by forcing CO2 into it. And then it bubbles out when you release that extra pressure because there's more CO2 dissolved in the water than wants to stay in the water. But carbonated water also tastes different than regular water, right? It's got a little bit of a bite to it. That's because when you force CO2 into water, you make carbonic acid. You actually drop the pH pretty significantly, even though it's just CO2 and water. By forcing them to react together, you make carbonic acid, which then drops the pH of that solution.
This is like why people ferment things just by sealing oxygen in something. And so that's why fermented things often feel carbonated.
Fermented things often become carbonated because, and it's not just that you're sealing oxygen in, it's that there's also microbes in there. That's what makes it a fermentation. So if you have the microbes will take the oxygen, but if there's not enough oxygen, they're not able to undergo full cellular respiration, aerobic respiration, and so they stop part way. So it's actually the same fermentation is the same process for why your muscles are sore after you work out. The lactic acid, you go through, if you do an anaerobic workout, like lifting weights or sprints or whatever, you wind up with a buildup of lactic acid in your muscles because your muscles ran out of oxygen to finish oxidizing the fuel source. If you do the same thing with microbes, you can make lactic acid, you can make ethanol, you can make all sorts of different products that and that's actually what pickling, making yogurt, making kombucha, making alcoholic drinks, they're all different forms of fermentation where all you do is you change what that microbe is and what its food source is.
That doesn't and that'd be dangerous.
It won't burn, but you can wind up with a buildup of pressure that will shatter a bottle. When I was homebrewing a lot, they call those bottle bombs. Basically, if you seal it into a bottle and you put an airtight cap on it before it's done fermenting, it'll keep producing more and more CO2. And if you do that too early, you wind up producing more CO2 than the bottle can handle. It's just the bottle shattering. But it is dangerous, but not that it won't burn. It'll just explode. Subtle difference, combustion and explosion, but turns out it's kind of significant sometimes. All right. So for these acid-base reactions, the easiest thing to do to recognize these is if you can recognize something that has an extra H plus that it can give away. Anything that you would name as an acid is a pretty good candidate for being an acid in a reaction. The acid is defined as whatever gives away an H plus. So acetic acid in this case is acting as the acid. Whatever accepts the H plus is called the base. And anything that doesn't really do anything in a reaction, like in this case, we had a sodium ion here and it's still a sodium ion over here. The sodium didn't really do anything. Call that a spectator ion. It's basically just there to balance the charge. You can't add bicarbonate without also adding sodium to balance the charge. So you always have the sodium there as well, but it doesn't really do anything. Sometimes though, you'll have a reaction where something that you wouldn't necessarily name as an acid can act as an acid. So for instance, if you put hydrogen carbonate with ammonia, it'll react and you make carbonate. And ammonium. We wouldn't necessarily think to name this as an acid. In fact, we wouldn't name it as an acid, but it has a hydrogen ion it can give away. And if it can give away a hydrogen ion, that's acting as an acid. And in this case, ammonia can accept an H plus. If it accepts an H plus, that makes it the base. Right. So if we're trying to recognize, I'm not going to ask you to complete the reactions and draw the product side yet. But for now, if I give you a reaction, I want you to be able to look at it and say, oh, that looks like a redox reaction because I can assign oxidation states. Or that looks like an acid-base reaction because I can tell that all that happened was my carbonate lost an H plus. Right. So it's not about completing the reactions at this stage. It's just about recognizing them. Right, and every combustion reaction will automatically be redox as well. Right. And so the way we recognize a combustion reactions are always something with a bunch of carbons and hydrogens plus oxygen gas, and it always makes CO2 and water. Sometimes there's some other atoms involved in there if it's not a pure substance. But so propane is C3H8 plus an oxygen. That's going to combusts to make CO2 and water. Obviously, this isn't balanced. But as soon as you see something makes CO2 and water as the products, and if it has oxygen as a reactant, combustion. So those are the easiest to recognize. And sometimes they can get a little bit more interesting. Like you can have, so C2H6O is ethanol. That burns too. Asen? I believe it's the quiz this weekend. I don't remember what I have to set up for the assignment for tomorrow yet. So it can be. Count your lucky stars. That's a good question. I had not thought about what the assignment was yet for tomorrow. I have to go back and check my assignment library and see what we had planned. So I know we're almost out of time, and it is a really nice day outside. So it's really impressive that everybody's been managing to pay attention as well as you have. The last type of reaction I want to talk about today is a precipitation reaction. This one's fast. A precipitation reaction is what you get when you mix two ionic solutions and they basically just swap ions. So there are some ions like phosphate that don't stay dissolved very well. If you put sodium phosphate, it dissolves in water pretty well. And then there's some cations that don't stay dissolved very well, for like calcium. So sodium phosphate is a stable solution. You can get it to dissolve. And remember, what that's really means is that you've got a bunch of sodium ions floating around and a bunch of phosphates floating around. Calcium chloride will also stay dissolved. So you've got calcium floating around with a bunch of chlorides floating around. As soon as you mix them, though, we get two new types of, or two new combinations, right? So if sodium's floating around, you could also have a sodium bump into a chloride. As soon as we mix them, we get sodium chloride. Does sodium chloride dissolve in water? Yeah. However, the other combination we can get is calcium with phosphate. Calcium and phosphate does not stay dissolved. In fact, that's one of the main components of bones and your tooth enamel. Calcium phosphate does not dissolve very well in water, which is a good thing, because that would not make for a very good tooth enamel if it did. So what happens when we mix these two solutions together is we still have sodium ions floating around and chloride ions floating around, but then we get calcium phosphate forming as a solid. So basically what a precipitation reaction is when you mix different ions together and you get a combination that doesn't stay dissolved anymore. So if everything is ionic and everything starts aqueous, but we make a solid, that's probably a precipitation reaction. In fact, precipitation comes from the same root as meteorology precipitation. Precipitation means you form something out of what appears to be clear. So in case of meteorology, it's like rain droplets forming, right? Or snowflakes forming from gas molecules in the air. In this case, you can take two clear, colorless solutions that just look like water, and when you mix them together, you get a cloudy, salt-looking thing forming at the bottom. It'll look like chalk, basically, in this case. So if you mix two solutions together and you get a solid, that's precipitation reaction. Does anybody have lime scale on the shower head at home? Like the little crusties that build up on the shower head? That's a precipitation reaction. That's what you get when you mix carbonate with magnesium or calcium. So our drinking water, our tap water, has calcium and magnesium in it. Not much up here in the mountains. Our water's pretty clean, but and that's why we don't have as much a problem with lime scale as other places do. But if you have some calcium and magnesium in your drinking water, when it gets exposed to air that has CO2 in it, some of that CO2 dissolves and you make carbonates. When you make those carbonates and there's already some magnesium or calcium in your water, it turns into a solid. So you make lime scale as a precipitation reaction. Anytime you've got like a buildup of something that just comes from water being washed over things over time, that's an example of precipitation reaction. And even like soap scum, that's actually the one of the components of the soap forming a solid with calcium and magnesium. Right, so recognizing these different reaction types, the reaction types overall are either not redox or redox. Rearrangement, complexation, pick your favorite term for those. It doesn't matter as long as you know they're not redox. And acid base and precipitation are two types that we're looking for there. If charges change, it's a redox reaction. If it's a combustion reaction, it's a redox reaction. So your quiz this weekend, I know that's a long time from now, will be on classifying reactions. I'm gonna give you some reactions. You just have to tell me what type of reaction they are. All right? I'll see y'all on Wednesday.
Thank you.